For the function f of x equals x plus cosine x, we want to determine the intervals where the function is increasing or decreasing. We want to find the local max and min values and the intervals of concavity as well as inflection points on the interval from negative 2 pi to 2 pi. So we'll start with the first derivative, f prime of x. The derivative of x plus cosine of x will be 1 minus sine of x. And so we'll begin finding critical numbers by setting our first derivative equal to 0, as well as thinking about where the first derivative does not exist, where the first derivative might be undefined. So setting 1 minus sine of x equals to 0, and solving, we'll have sine of x is equal to 1. Now remember, on the unit circle, if we're thinking about sine, we're interested in the y value. And the y value on the unit circle will equal 1 up here at pi halves. However, we're considering the interval from negative 2 pi to positive 2 pi. So we also need to consider the negative angle around here, which would be negative 3 pi halves. So we have two x values in the given interval. One is negative 3 pi halves, and the other is positive pi halves, where sine of x will equal 1. So now we'll do the first derivative test, and we're going to check the sign of the first derivative around these critical numbers. So around a negative 3 pi halves and positive 3 pi halves. However, since we're also working on a restricted domain here between negative 2 pi and positive 2 pi, I like to put those values on my number line as well, just because I like to have a visual reminder that there's no need to test anything smaller than negative 2 pi or greater than 2 pi. So I actually X those out on my number line as just a visual reminder. So now we're going to choose our test values. So we need to choose a value between negative 2 pi and 3 pi halves. Again, if you visualize that on the unit circle, we're talking about a value between negative 2 pi and negative 3 pi halves. So I need something here in the first quadrant, but of course in the negative direction. So something like negative 7 pi fourths would work. And then I need a value between negative 3 pi halves and positive pi halves, So 0 would be good, and nice easy value. And then something between positive pi halves and 2 pi, and there's a number of possibilities here. I'll just use pi. Now remember, we're taking these values and we're testing these into the first derivative. So these test values are coming up here into 1 minus sine of x. And you can grab your calculator to do this, or of course, we've chosen nice values here. You know, a negative 7 pi fourths has a reference angle of 45 degrees, so technically that should be one that we're able to compute in our head. Otherwise, pause the video, grab your calculator, and I want you to substitute these critical numbers, these test numbers into your first derivative. So when we substitute in negative 7 pi fourths, we should end up with a positive value. When we substitute in 0, that's also going to yield a positive value. And when we substitute in pi, that should also yield a positive value. So this is interesting because the derivative is always positive here, and that means that the slope of the function is always positive, which means the function is always going to be increasing. So we can go ahead and answer the question for increasing. This function is going to increase for all x values between the given interval, which was negative 2 pi to positive 2 pi. And I'm not going to include those endpoints because we're not considering anything on the other side of negative 2 pi or anything outside of this interval. So I'll use parentheses here to say we increase from negative 2 pi to 2 pi since we don't have any certainty about what's happening on the other side of negative 2 pi or positive 2 pi. And therefore, it's never decreasing because we don't have any negative derivatives. And since there's no change in sign for the first derivative, then that means that we don't end up with any local maximum or minimum values. So I'll go ahead and just write none. So now we're going to move on to the second derivative so we can analyze concavity. So the second derivative is the derivative of the first derivative. So the derivative of 1 minus sine of x will be negative cosine of x. And then we need to analyze where the second derivative may change sign. So we're going to branch off because we know that a function can only change sign at zeros, at its x-intercepts, or perhaps at places where the function is undefined. So we're doing the same thing we did before essentially, but now with the second derivative, we're looking for places where the second derivative is equal to 0 or where the second derivative is undefined. So negative cosine of x is equal to 0. That will be when cosine is equal to 0. And we have quite a few values where the cosine is equal to 0 if we're looking at the unit circle between negative 2 pi and positive 2 pi. So remember, cosine is the x value on the unit circle, so we know that cosine will equal 0 up at pi halves and also down here at 3 pi halves. But we also have to recognize the negative values since we have to go in the negative direction as well. So that would be negative pi halves and then all the way around here to negative 3 pi halves. So I'm seeing 4 different values here that we're going to have to test around. We have a value of negative 3 pi halves, negative pi halves, positive pi halves, and then positive 3 pi halves. And I'm out of room, so I'm going to have to move a little bit here to the right. So we're going to go ahead and create a number line and do a little analysis on a second derivative. And again, I'm going to go ahead and include negative 2 pi on my number line just as a reminder that I don't want to choose a test value that's smaller than negative 2 pi. And then I have a lot of values here that I'm going to have to test in between. So negative 3 pi halves, positive pi halves, or negative pi halves, positive pi halves, and 3 pi halves. And again, I'm going to put positive 2 pi here on my number line. I'm also going to get out my red pen. I'm going to X out everything smaller than negative 2 pi and bigger than positive 2 pi, just as a reminder so that I don't accidentally choose a test value in those intervals. So now we've got to choose a test number between negative 2 pi and negative 3 pi halves. So thinking about where that would be. So negative 2 pi would be all the way around the unit circle in the negative direction, and then negative 3 pi halves would be putting me here on the positive y-axis. So I need to choose a test value, an angle that's somewhere in the first quadrant, that terminates in the first quadrant, but it has to be a negative angle. So there's a variety I could choose. I like reference angles of pi fourths. I think they're easier to remember. So I'm going to choose negative 7 pi fourths. Then we need a value between negative 3 pi halves and negative pi halves. So I'm going to choose negative pi. Something between negative pi halves and pi halves, a good one might be 0. Then I'll choose pi, and again, positive 7 pi fourths. So once again, this is going to be a time where you grab your calculator, unless you're going to do this computation in your head, which you could do. We're testing into the second derivative. So we're going to take all these test values and we are substituting these values up here into my second derivative, which is just negative cosine of x. So the negative cosine of negative 7 pi fourths will give us a negative value. The negative cosine of negative pi is a positive. The negative cosine of 0 is negative. And again, this is a point where you really need to do this computation on your own. Don't just take my word for it and keep watching the video and just take my signs here. Make sure you're actually computing these on your own and verifying that you indeed do get the same thing that I'm getting here with our signs. So our signs look to alternate here on my second derivative, so we have a lot of different changes in concavity. So remember, a negative second derivative means that the graph is concave down, and then a positive second derivative means the graph changes to concave up. So every place that we have a change in concavity is going to be a little inflection point. Since all of these values that we were testing around, they're all in the domain of the original function, because the domain technically is all real numbers, but we're restricting ourselves between negative 2 pi and pi. That means we end up with 4 inflection points for this graph. This is interesting, 4 inflection points. We'll have to come back in a second and take a look at the actual graph. So using this analysis on the second derivative, we can answer where the graph is concave up. So there's going to be quite a few intervals here. So our graph is first concave up from negative 3 pi halves to negative pi halves. And then we are going to be concave up again from pi halves to 3 pi halves. And then we have 3 intervals where we're concave down. So first interval, we're concave down from negative 2 pi to negative 3 pi halves. Second interval, where we're concave down, is between negative pi halves and positive pi halves. And then the third interval, where we're concave down, looks to be between 3 pi halves and positive 2 pi. Now, when you go to answer the inflection points, remember, we don't just want the x values. These are actual points on the original curve, so these are going to be coordinates. So I'm going to write them as coordinates where we were going to fill in the y value in just a moment. So negative 3 pi halves, negative pi halves, positive pi halves, and positive 3 pi halves are all the x values of our inflection points. But then we're going to need to substitute these x values all the way back into the original function. So I'm going all the way back to the beginning here into our original function, which was f of x equals x plus cosine of x, because we want to find the corresponding y values on the original function. So you need to input negative 3 pi halves back into the original. We're going to have some decimals here. You can certainly use your calculator. Just round to the nearest hundredth, I think, is sufficient. So when you substitute in negative 3 pi halves, I'm getting a y value of negative 4.71. Negative pi halves gives us a y value of negative 1.57. Positive pi halves gives us 1.57. And 3 pi halves looks to give us positive 4.71. So these are our 4 inflection points. So the very last thing I would love for you to do is to grab out your graphing calculator or open up Desmos and actually graph the original curve. And let's take a look at the graph and see if the graph corresponds with what we have for our analysis here. So I've used Desmos here to graph x plus cosine x. And I chose a window from negative 2 pi to positive 2 pi, and I chose a y value range from negative 8 to positive 8, just so I could check this out and see if it correlates with what we've had so far. So notice the graph is indeed increasing the entire time, so we don't have any maxes or mins. And then we also have this place here where the derivative is equal to 0. See where we have a horizontal tangent? And sure enough, that corresponds to about negative 3 pi halves. And that indeed was our first inflection point. See how the graph changes? The shape, the curvature of the graph, it changes from concave down, and then here it goes to concave up. And then we have a change again to concave down. So it looks like we do indeed have one more inflection point. So we have an inflection point, somewhere in here. Let's change colors for you, sorry. Somewhere in here would be our inflection point, which that corresponds to about negative pi halves like we thought. And then we have another place here where the first derivative is equal to 0, and the curvature also changes again. So that would be our third inflection point. That one was about pi halves. And then you can see, it's kind of hard to see because of these setting features here in Desmos, but we would have one more inflection point. So this graph goes from concave up, and the very end of it changes to concave down. So somewhere up here we have our last inflection point as the graph goes concave up, and then we have that last change to concave down at the end. So it's always good to verify that our graph does indeed match our analysis at the very, very end.